Hi, and welcome to another exciting edition of Stat 200. We're going to talk about the material from Lecture 10. That's more stuff on probability, discrete probability, in which almost always you have a finite sample space, a finite number of possible outcomes, and the outcomes all are equally likely. Watching this video, as always, does not substitute for reading the book and notes. Those are your primary materials, and this is a supplement. Okay, first of all, I want to talk about conditional probability. It's written this way: the probability of F, and then a little stroke, and then E, and that's read the probability of F given E. E and F are events, of course. This is the probability that F occurs given that E occurs. So you're allowed to assume that E occurred and then compute the probability that F also occurs. Now, if you took a look at a Venn diagram here, think about this a moment. Here's the event E, and here's the event F. And there are going to be some outcomes. There are outcomes in E. Maybe there are outcomes in both. And there are outcomes over in F. When you're computing the probability of F given E, that means you get to assume that E has occurred. So really, the whole sample space now consists of just E. You ruled out all the other possibilities. And if these were all equally likely to begin with, and we're going to assume that that's true here, then all the outcomes in E are equally likely. It's as though you change the problem to look just like this. Right? Here are the outcomes in E, and the question is, are they also in this little part of E, which is, of course, F intersect E? So if you think about it this way, the general formula for the probability of F given E, which is probability of F intersect E over the probability of E, makes perfect sense. First, probability of E, that's the probability you select one of these outcomes, selecting at random, and then the probability of F intersect E, that's the probability of these little guys happening, given that, divided by the probability of E means given that you've chosen one of the outcomes in E to begin with. In any case, this is the general formula for the probability of F given E. Okay, let's do a couple of simple examples of computing with this thing. An urn contains 6 red marbles labeled 1 through 6 and 6 green marbles also labeled 1 through 6. E is the event you get a green marble, and F is the event you get a number higher than 4. One marble is chosen. So we're going to be asked to find probability of E given F and the probability of F given E. Okay, we're going to go with the formula here. The probability of E given F is going to be the probability of E intersect F divided by the probability of F. So we need each of these. Let's just go over here and see what's in those sets. E intersect F, well, to be in E intersect F, the outcome has to be get a green marble and a number higher than 4. So it's going to be the green 5 or the green 6. So I'm just going to write it that way, G5, G6. Right? That's all that E intersect F contains. So this says the probability of E intersect F is 2 out of 12. There are 12 outcomes altogether, the 12 marbles. They're all equally likely. 2 of them are in this set, this event E intersect F, and so 2 twelfths or 1/6. What about F? What's in F? F is the event get a number higher than 4, so that could be the red 5, the red 6, the green 5, or the green 6. And so probability of F easily 4/12 or 1/3. And then from those, we can calculate the probability of E given F. So it's just going to be 1/6 divided by 1/3, which is 1/2. If you have difficulty manipulating fractions, dividing them or whatever, just use your calculator and get the decimal equivalent. Okay, how about the probability of F given E? That's going to be, by the formula, the probability of F intersect E over the probability of E. Now, F intersect E is the same set as E intersect F. So this numerator here is going to be the same as the numerator up there, 1/6. The denominator is the probability of E. And that's very simple because E is just get a green marble, and 6 out of the 12 marbles are green. So probability of E is just 6 out of 12, or 1/2. So the denominator here is 1/2. And when you divide those, you end up with 2/6 or 1/3. Okay. Here's another one. Conditional probability from a contingency table. These are actually usually easier to compute than the other sort. This table here is, it shows some stuff about the New York Mets season, 2017 season. It's divided into the rows home and away, how many games were played home, 81. 81 were also played away, and wins and losses. They won 70 and lost 92. And that means they played 162 games altogether. Now suppose you choose one of these games at random. One of these 162 games. What's the probability the Mets won it? Well, looks like they won 70 out of 162, so we say the probability that they won is 70 over 162. What's the probability that they won given that they played at home? Now, I could write out, events, W and H and so on, and use the formula, but I'm actually going to do it a way that I usually find easier. We're going to find out the probability that they won given that they played at home. If they played at home, we can ignore everything but that top row. Once you know that they played at home, it's only those 81 games played at home that matter. And they won 37 of those, so the probability that they won, given that they played at home, is just 37 out of 81. That's why I said problems involving contingency tables are often the easiest sorts to find the answers to. We got one more question here. If they lost the game, what's the probability that they were playing away? Well, if they lost the game, then we're talking about the games in this column right here. There were 92 of them. How many of those did they lose? They lost, oops, I didn't mean that. How many of those were they playing away? They played 48 of them away. So if they lost the game, they must be in this column. And then of those 92 games that they lost, 48 were played away. So the probability we want here is 48 out of 92. All right. Next topic related to this is about independence. Independent events. And we say that two events, E and F, are independent. Properly speaking, they are statistically independent, but we usually just say independent. They're independent if two things are true. The probability of F given E is the same as the probability of F, and the probability of E given F is the same as the probability of E. But what does a thing like this mean? The probability of E given F is equal to the probability of E. Well, the probability of E is something that you calculate without reference to F. It doesn't matter whether F occurred or not. There doesn't even have to ever be such an event as F to compute the probability of E. Right? And then if you compute the probability of E given that F occurred, it doesn't change anything, meaning that whether or not F occurred doesn't change the probability that E occurred. And this says exactly the same thing about F. The probability of F is unchanged, whether E occurred or didn't occur. See? So intuitively speaking, two events are independent if either one happening doesn't change the probability that the other one happened. Okay. Regardless of whether E and F are independent, we can get a formula for the probability of E intersect F. It is the probability of E times the probability of F given E, and it's also the probability of F times the probability of E given F. Right? And that just comes from the previous formula from multiplying through by the denominator. Now, it is a true fact, right? Here it is, true fact, we can't prove it in here, but it is a true fact that two events E and F are independent if and only if, right, IFF, if and only if the probability of E intersect F is equal to the probability of E times the probability of F. That should make sense to you because E and F are going to be independent. For example, if they are independent, then the probability of E given F is the same as the probability of E. Right? And so the probability of E intersect F is just probability of F times the probability of E. And the same with this one over here. Okay, let's do a simple example with that. So let's suppose that we roll one fair die, and that'll be a six-sided die, of course, and flip one fair coin. And what's the probability? The probability of getting heads and a 4. So heads on the coin, 4 on the die. I want to do this two different ways, actually. First thing I want to do is write out the entire sample set. Right? You got a coin, you got a die, so you can get heads and a 1, heads and a 2, heads and a 3, and so forth. And the same thing for tails. Okay, that's the whole sample space. The event heads and a 4, the only outcome in that event is this one right here, right? Heads and a 4. So the probability of heads and a 4 is the probability of the event containing only the outcome, H4, right? And that is 1/12. These are all equally likely because the coin and the die are both fair. So that is the simplest and most straightforward way to do this. Let's do it with the using this fact right here. E and F are independent if and only if that equation holds. So to do that, we have to think about whether these two things are independent. Right? So let's go ahead and make definitions so that I can talk about them sensibly. E is going to be the event to get heads on the coin, and F is going to be the event you get a 4 on the die. Are these independent events? Well, think of watching me flip the coin and roll the die. Right? I'm doing it in a box so you can't quite see. And I cover up the coin and I tell you there's a 4 on the die. Right? What's the probability of heads on the coin? It's still exactly 1/2, right? Knowing what happened to the die does not change the probability of getting heads or indeed getting tails on the die, on the coin. And it's the other way around. If you covered up the die and saw heads on the coin, you still wouldn't know what, it wouldn't change, rather, what the probability of getting a 4, or any other number for that matter, on the die was. Those two things are independent. Either one occurring, knowing you got heads doesn't change the probability you got a 4, and knowing you got a 4 doesn't change the probability you get heads. So those are independent. Right? E and F are independent. So I can use that formula. The probability of E and F, right, which is what we're looking for, heads and a 4, is then the probability of E times the probability of F, because these things are independent. E is the event get heads, so the probability of E is 1/2. F is the event you get a 4, so the probability of that is 1/6, and multiply those and you get 1/12. Okay, let's do one more of these. I want to do this two ways too. A bag contains 5 red marbles and 4 blue marbles. John draws out a marble and then draws out another marble without replacing the first. What is the probability that both marbles drawn are red? Okay, first thing I'm going to do is I'm going to try to just think my way through this. So when he's got 9 marbles altogether, 5 red and 4 blue. So when he draws out the first marble, what's the probability the first one is red? So let's say R1 is the event the first marble drawn is red. And we'll let R2 be the event, R2 be the event that the second one is red. So what's the probability of R1? The probability of R1, the probability of drawing a red marble out of that bag on the first draw, the probability of R1 is just going to be 5/9, because there are 5 red marbles in a bag of 9 marbles. Now, the probability of R1 and R2, which is what we're looking for, that's going to be the probability of R1 times the probability of R2 given R1. All right, we already know this one. This is 5/9. What's the probability of R2 given R1? Well, given R1, that means you drew a red marble out of the bag on the first draw, and you don't replace it. So the bag now contains only 8 marbles, and only 4 of them are blue. So the probability that you draw a red marble on the second draw, given that you drew a red marble on the first draw, is 4/8. And this multiplies out to be 5/18, not that it really matters here. Okay, let me show you another way that people think about this, a way to make it an explicit representation that may make it easier to think. What we're going to do is we're going to make what's called a tree diagram. We're going to have a root, which just corresponds to where you begin choosing. And then we're going to have 2 columns. We're going to have a column for the first draw, and we're going to have a column for the second draw. And it is just a matter of thinking it through, just like the other one, right? But with a picture that kind of helps. Now on the first draw, you can either get a red marble or not get a red marble, which I'm going to symbolize that way. And on the first draw, there are 9 marbles, of which 5 are red, so I can label this branch with 5/9, the probability of drawing a red. And then this would, of course, be 1 minus that, or 4/9. On the second draw, I can either get a red marble or not. This path right here would represent, not getting a red on the first, but getting a red on the second. Right? So you think of moving from the root out toward, these things are called leaves at the end here, moving from the root out along some path toward a leaf. Right? And the path that we're interested in is this one right here, red on the first, red on the second. If this happens, if you draw a red on the first, then you have to stop and think, okay, now I have 8 marbles altogether, and only 4 of them are red, so the probability of drawing a red on the second draw would be 4/8. Of course, this would also be 4/8 because these two have to add up to 1. Either you draw a red on the second or you don't. Similarly with this one, if I were to label these 2 paths, let's see, if you draw a non-red marble, then you still have 5 red marbles left out of 8. So this one would be 5/8 and this one would be 3/8. But this is the only path we're interested in this problem. And I can get the probability that this process takes a certain path by multiplying the probabilities along the way. So the probability of this, the probability of red then red, right, which is exactly what we were computing up there, is 5/9 times 4/8, just as it was up there. All right, that's about it for this section.